Hello, Kennedy. Nice seeing you online. Okay, so here are the lists for presentations, and sometimes the file is named EC, but it is not EC. It is equivalent to midterm or whatever, and it is major contribution towards the grade, more important than the lecture materials, because it is practical skills that really will help you in real life. So there were 3 people who didn't vote, and then I assigned. So Kennedy, please consider to present number 5. I didn't saw your votes. So, and the materials are available on the recordings of the lab from the Wednesday. And 2 subjects. I don't know if Adam and Tim are already connected or watching in the recording, so please plan on presenting 7 and 8. The slide, the presentation is 4 minutes. Slides are due Sunday to Monday midnight, because I want to evaluate before listing them, maybe provide some quick feedback for improvement, and I want to have them all ready, even if you are sharing, if you are coming online and sharing your screen, just in case I want to have a backup, because the importance of these presentations is not only for me evaluating and helping you to progress towards grade, but it's also a reminder to those who are not able to attend this or that lab of the vital subject, vital skills that will be, everything you do after will be based on this stuff. So one was not able to complete the course without being mastering the skills. Okay. So, and here's the little homework that I've heard that there are several people who are submitting it today for doubling the credit. Here are the points for regular credit, and we will discuss. I will announce the answer key on Wednesday. So please send it before Wednesday. I'll send a reminder. This is not the most challenging work, right? And I apologize for bothering you with homeworks, but we need to have some. So this one will be in not coming Monday, but next Monday, and I will announce it through as we go through the week. Okay. Let me check quickly with Kennedy if there are any. Oh, I will see the. Oh, hello. I see your text. Okay. And I believe the vision of the camera is okay. If needed, I can share the screen, but I want to take an opportunity to point on the places which is easier to do in person. Okay. And let me give a few words of what we are doing. So, first half of the class, we were believing that only electrons have Lyavian nature. And by using mathematical tools, like a range of different tools, we were able to describe Lyavian nature of electrons in molecules, or at least we opened the door. And we approximately know what to do if you want to describe Lyavian nature of molecules and predict their properties. I think our best accomplishment in the first half was the quantum confinement stuff. Maybe you have different vision, but later on, one definitely needs to be more precise with potentials, and the goal, if one walks on the way towards electronic properties, is hydrogen atom. This is like fundamental for all modern science. But we need to pump our mathematical muscles more because it is truly hard, even if in reduced shape. Although all of us had it in either freshman chemistry or high school, like SPD orbitals, but math for it quite deadly. And you better postpone it, focus on wavy nature of nucleus, how the interatomic distance can be represented as a wave function, and are there any consequences for realistic observations. We did agree that potential near equilibrium is quadratic, and then we set up the time-dependent Schrödinger equation with this potential kinetic energy. My hidden wish is to do time-dependent thinking in everything. But before we are able to jump onto this level, we need to master everything which is possible with time-independent properties of the oscillations, like find eigenstates. And the meaning of this eigenstate, like the ground state, means that there is a probability distribution. Interatomic distance can be a little longer and a little bit shorter with different level of probability. And if one excites, and if you know that it exhibits quantum properties, then it will have bigger energy and it will have different probability with this 2 humps, 3 humps stuff. Also, by looking back onto orbitals, eigenstates, wave functions for particle in the box, we did observe the trend that the higher the energy, the larger number of fringes, the denser are the fringes. Same as in plane, in the free space. The quicker the motion, the denser the fringes. The same trend holds everywhere. So for oscillator as well, if you go higher, it is more peaks and more nodal points. We skip traditional way of getting these eigenstates through special Hermitian functions, and instead we accept a little bit more scientific rather than mathematical way through creation and annihilation operator. We were implying this strawman that can go up and down on the ladder, and then we accept the philosophical idea if this straw character wants to jump lower than the ground, it is not possible. It will give 0. By this, we got quite simple equation for the ground state, and now we generate excited states by applying creation operator. Creation and annihilation operators are composed as superposition of position and momentum because square of them should give position square and momentum square. So we went through the way how to get this stuff. Next step, we are generating eigenstates and then normalizing them. The reason to normalize eigenstates is to establish relation between actual eigenstates and creation operators and factors. By acting with creation and annihilation of an operator, one not only promotes the state up or down on this ladder, but also adds a factor. This factor, which is like square root of number of state, is important on our next jump, next step, when we are going to transfer all operators from continuous, discrete, and differential operators to discrete set of levels and operators that describe transitions between them. So we will be able to convert all operators like position, momentum, energy into the basis of discrete states. And a lot of substantial number of problems will be much easier. And understand some level of natural irritation on the other side of the trench when like I see a new homework, you see a new homework again, I need to spend time. So there is a little reason for the homework that is you are submitting now, or someone will submit on by Wednesday, and the next one. So these homeworks complement the stuff that we cannot fit into the quite tight class schedule and help us to make a transfer from continuous wave functions to discrete representation for harmonic oscillator. There, I believe, I know, I hope, and then I advocate that discrete representation will be much easier. But the transition to discrete representation is quite laborious, and at least to believe in it, one needs to practice some steps. What are we going to do? We're not going to do anything substantial today. I will just prepare, like we are taking ramp and taking momentum to jump to the discrete states, and I will just mumble some auxiliary things, preparing for this transition. And the homeworks are also preparing us for this transition. If we briefly look back onto the homeworks, so the one here is a third way to generate eigenfunctions. We used, there is a first way just to find eigenvalue problem for Schrödinger equation. Second way is creation inhibition operator, and the third way is just to apply so-called Rodriguez equation. And the homework that will be in like a week and a half from now, it already deals with details of expressing the operators like creation and annihilation in form of a matrix, then expressing the position and momentum in form of a matrix. So you do not need to know today, you just give it a little heads up what is our plan. So here is where we ended last time. So by applying creation operator to number one, we're getting state number two multiplied by factor. And by extrapolating this result and believing that this trend will hold for next states, we tell that applying creation operator to eigenstate of harmonic oscillator number n, we will get state number n plus 1 multiplied by square root of n plus 1. Let me quickly go online and make sure that Kennedy, if you want any comments, if you have any questions, please let me know. I'm here to give them. Comments 1, comments 2, comments 3. No comments. I'm going further. So, in some sense, it is question number one of the very next homework. We're answering now, and you will need just to copy paste. So, if I do accept an idea that applying creation operator to eigenstate number n will be state number n plus 1 with a factor. Now, my interest, my goal is to jump from continuous space to discrete space, to represent each operator as a matrix. So, and our ideas and our discussions before were, if one does have an operator and one applies state, eigenstate, crazy state from the left and right, one is getting matrix element, right? So we want to practice the same thing here. So by now, our understanding of this creation operator that it is some x minus ddx with some factors. So it is differential operator. But we want to convert this differential operator into the discrete space. And instead of like if I would be too traditional, if I would want to torture either myself or the class, if I didn't introduce this creation and initiation operators in the differential form, I could use an operator and then put explicit form, like for phi naught, I would put this e minus alpha x squared over 2. Here I put operator, here I would put like 2 alpha x minus 1 times e minus alpha x squared, and then integrate, right? This is possible, and this some textbooks do have it as an exercise, but we already made some effort, and we know this property. By applying operator, we do not have operator anymore, we have just changed state. And now if we multiply this cap by an arbitrary bra, we should be able to practice orthonormality relation. I didn't rigorously introduce it here for oscillator, but we want to believe, and if you really need, we can prove that any good basis matches if the states are normalized. If it is a good solution, they should be orthonormal. So convolution of states with coinciding numbers will give 1. With non-coinciding numbers will give 0. And n equals either 1 or 0, right? So here we have convolution of our n plus 1 and n. We can just write down this orthonormality property in the n. And here we can tell that it is delta function with indices m, comma, n plus 1. And if you accept this notation, then the matrix element of the creation operator will be delta function mn plus 1 times this stuff. So how to convert delta functions into matrices? What if we have delta mn without this stuff? Which matrix would it correspond to?
First matrix.
Huh?
The first matrix.
What do you mean first matrix?
Mn. Corner.
Which corner?
Bottom left.
So let me reformulate the question. So if I do have a Kronecker delta mn, it is a set of numbers, right? It is an object with two indices. So you can tell that it is a matrix with some elements. What are the values of these elements? Can they be 2 or minus 1?
0 and 1.
0 and 1. Okay. And where this 0 and 1 are
Diagonal.
yes, it was the question. I just maybe didn't formulate it in a right way. So on Zane told that, Jared, do you agree?
Yes.
Right. So it is ones of on the main diagonal and zeros everywhere else. So delta function is, and some people call it unity matrix or identity matrix. Now we do want to express this matrix element in the same form. How would it look like? It's the result of the answer. I need to insert new slide and draw it. Otherwise, it will be too boring to just go over slides. So we have m plus 1 delta m comma n plus 1. So we need to agree what is our m, what is our n, or do we what counts rows and what counts columns? I always forget it.
M is the row, N is the column.
Huh?
M is the row,
Okay.
N is the column.
Okay. So if m equals 1, so first row, and n equals 1, which means second column, there should be 1. This stuff will be 1. So if m equals 1, n equals 1, but n plus 1 will be 2. We are looking for the first row and second column. And delta function will be 1. But we need to multiply it by n plus 1. So it will be square root of 2. N equals 1, n plus 1 equals 2, square root of 2. If you find me wrong, you'll get extra credit. So be critical.
Would that be our bottom state?
Huh?
Would that be our bottom state? So wouldn't m and n equal 0? And then your
No, we start from 1.
square root of 1.
Because we do only 0. If you start from 0, then
That would be square root of 1 on the top. And then column 1,
okay.
row 2
Okay.
would be
Okay,
square root
let's
of
start
2.
from 0. Start at 0. But
And it would be 0, n plus 1 would be 0 plus 1, square root of that would be square root of 1.
okay, so we'll put it here. Okay.
And then,
Square root of 2 will be here.
yes,
And square root of 3 will be here.
yeah.
And
And then
the
it'd be
main diagonal will be zeros,
yeah,
and
then
everything
zeros.
else will be zeros as well. So,
How would it be zeros? If you do n plus 1, your first n would be 1, right?
no.
So you square root-
Any time we need m equals n plus 1 or n equals m minus 1. It can happen only once per row and once per column.
Okay.
This is I'm confident.
Okay.
Okay, so let's Zane plus 1. And the things here will differ if we swap the creation by annihilation. So the creation and annihilation are obtained from each other by transposing operation, right? And the only difference between them is that rows and columns are swapped. Is it the time I was planning to do the little quiz? I hope no. I'm not ready for it. We'll do it some other time. So the only thing I can try to remember that when there is a plus here, there is a minus here. And absence of sign, it means going down, so it's equivalent to minus, but then we have plus. And an interesting observation is that if one adds this, the superposition of position of moment operator gave us either creation and annihilation. Now, if we superimpose creation and annihilation, if we add them together, then this plus and minus will subtract, and we will have only x. And then if we divide everything by appropriate, by the square root and 2m omega, we'll get that adding together creation and annihilation with some factor will give us the position operator. Algebraically, it's like boring and nothing interesting. But if you try to imagine this as human, just philosophically, it looks crazy. Operator of position, where a particle is located, means summation of going up and going down in the eigenstate. I don't want to think about it just for my mental sanity. But algebraically, it is what we get. And later on, one can get healthy benefits out of this property. So I wouldn't recommend to think and analyze how to interpret it, but the property is that wherever we need to work with a position operator, we can replace it by summation of creation and annihilation. And one can do the same trick wherever we need to play with momentum. One can use subtraction of creation and annihilation. So it's in many, I wouldn't say application, in many ways to describe applications by pen and paper, by equations, it is a beneficial shortcut. Okay, another property on the way to converting everything into discrete representation. And stay ready to catch my errors. So if our creation, did I introduce this equation? Do you need it or you believe it? I believe it. Do you want to believe it or you can derive it? Okay. But what is your feeling? Like, is it evident or just looks trustable? It looks trustable. Oh, okay. I thought so. So each of any operator, especially in the discrete form, is dyadic product. When we have scalar product, we have bra times ket. Here, our bra and ket are swapped. So it means this stuff acts on a wave function that we assume may stay here, and then converts it into a wave function that appears after we apply it. Right? And we know that it converts state number n into state number n plus 1, and it assigns additional factor, square root of n plus 1. Basically, it is what we proved or attempted to prove last time, and what is the extra credit question 6 in the homework. If we are doing inverse operation, if we do annihilation, we are jumping from state m to state m minus 1, and we are getting factor square root of n. And this if you want to go lower than 0, you get square root of 0, so this operation will not work. So kind of logically consistent. Now, I was introducing the idea that product of creation and annihilation should be equivalent to energy, because position squared and momentum squared are energy with some factors. For harmonic oscillator. And it is basic idea that we used at the beginning. Now I want to return to this idea as if, like, suppose house pets have very short memory. Suppose I'm such a creature that cannot remember what happened more than 10 minutes ago. So suppose I do not remember how I came to the explicit expression for the creation of annihilation operators, but I just want to practice multiplication of these operators by each other and observe consequences. So the expected surprise, depending on whether I'm remembering what I was doing before or not, will be that by applying creation and annihilation right after each other as a product, one should arrive back to the same state. Make sense? But in addition to arriving to the same state, one is getting additional factor. And this factor is equal to the number of states. And if I multiply these two operators by the energy constant, like frequency of the oscillation times Planck constant, then applying annihilation and then creation and then multiplying by energy, we'll get the higher energy. The higher was the number of the state. So basically, I'm trying to use some bypass ways to come to the statement that product of these operators plus 1/2 because of the commutation we can show later will be equivalent to operator of total energy, and we can practice it. Hamiltonian, just in case it's total energy. So I would be really interested to multiply these two things and observe what happens. This looks ugly, and I can reproduce ugly writings anyway from scratch. So it would be really interesting to see if multiplying two operators in this discrete representation will follow our vision of energy, which should be like diagonal matrix with those raising up. What can I do to this expression? And what in my time when I saw such expressions first, reaction was fear, because we all were trained in high school and calculus to do derivations with continuous functions, and this is more like merger of linear algebra and it's just linear algebra, but not in the graphical form of matrices, but in the derivations. So this is one matrix, this is another one, and we need to multiply. And then after getting some practice, one may arrive to the idea that these operations with matrices in algebraic way is much simpler than any other tasks one has to do in this activity. Okay, so what can we do practically? First, I can pull summations on the top, because it's swapping of the terms in summation doesn't change stuff. So summation over m, summation over n, square root n plus 1, square root n. And then I do have n plus, no, this should be n. So we do have a long sequence. Cat, oh, this is bra. Bra, cat, bra, cat. Too many of those. We know from linear algebra that multiplication of two matrices should be another matrix, like object with two indices. We kind of arrive to an idea from this physical chemistry quantum theory that product of two operators should be another operator. And operator is just one bra at the right and cat at the left. And we know that multiplication of two basis functions by orthonormality is should, like, scalar product should give a number, right? So we plan to perform this convolution and get rid of this element. And this will be delta m comma m minus 1. So, which means that how do we interpret replacement of this stuff by the delta function? It means n equals, it will be non-zero when n equals m minus 1 or when m equals n plus 1. It means we need to get rid of all elements except those where such relation between indices hold. And I see immediately that if we apply the stuff, one of the summation signs should disappear. So if I decide to keep n and remove m, then I need to practice this one and replace m by n plus 1 everywhere. So instead of m, here I would have m plus 1. Instead of m, here I will have m plus 1. So letter m comes 2 times here and there. And I'm going to replace it by n plus 1. So summation of m, I'm just trying to look what I had and then trying to translate it to the next slide. Then square root of n plus 1, then square root of n plus 1 once again, right? Because I did this replacement. Then I will have n plus 1. Then I have nothing because summation and delta function delete each other. And then we used to have m, but I will replace it to n plus 1.
So it's n plus 1, n plus 1, n plus 1.
Exactly. And no one cares. I can do a little trick and call n plus 1 another variable. And then tell that it will be summation over k. This multiplication will remove the square root, right? It will be k, k, k.
And then your summations over k, not n, right?
Exactly. Thank you. Zane plus 1. Let's check online if there are. I think we did scare someone, or maybe there was a scary content. So it means this operator will convolute this state k and convert it into state k, which means it will not change anything. In some sense, this one is like diagonal operator. And then one would accumulate a factor linearly raising with the number of states. So basically it will be a matrix with only main diagonal with elements increasing. Oh, I had a little better writing, but I think we arrived to the same conclusion without working on this written stuff. And I'm not going to give details right now, but later on we will come to them. To be literally in agreement with pure Hamiltonian, one needs to add 1/2 here. And this 1/2 corresponds I do not like to declare things without proof. Suppose we take our old-fashioned total energy operator with positional parameter. Suppose we take our eigenfunction for the ground state. Suppose we take matrix element of Hamiltonian. We will obtain h bar omega times 1/2. So the energy of lowest state will be 1/2 multiplied by frequency. And the frequency corresponds to the steepness. The steeper, the higher the energy. Same as quantum confinement for the particle in the box. The smaller the box, the higher the energy of the lowest state. And this 1/2 is needed to reflect the same property which corresponds to quantum analog. It is an analog of quantum confinement for harmonic oscillator. So this 1/2 needs to be here. And then we run up, it just increases by 1. Which means if you represent total energy operator as a matrix, it will be this frequency factor, and then 1/2, 1 plus 1/2, 2 plus 1/2, 3 plus 1/2. And in this style, the Schrödinger equation and all other tools become much simpler. Let's watch the time. Oh, okay. And wave functions can be like if it is state like number 2, it is just expansion coefficient 1. I want to believe that it is the last one. Okay, thanks much. I look forward to see your early homework if you want to. Optional, just for extra, and the presentations mandatory. Right? And of course, I want to see you on Monday. Right? Okay, meeting is done. Everyone is welcome to disconnect and depart. Have a nice weekend, and let me know if there are any questions I can answer.
And then position operator squared minus momentum operator squared, is that total energy operator?
Position squared plus momentum squared.
Is
If you want to exaggerate and simplify, one needs to get like momentum squared divided by 2 mass.
okay.
And position squared multiplied by mass frequency squared divided by 2.
Okay. But it's total energy
Right.
operator?
Yes.
Okay.
4 harmonic oscillators.
Or harmonic oscillator.
Thank you. Thank you.
Thank you.
My pleasure.